Hi, and welcome to the 13th lecture of Introductory Astronomy. Today we'll be talking about the interior of the sun. Last time we talked about the outer parts of the sun. So first off, this is being taped actually on Monday, not Wednesday, so students couldn't stay. They actually had to go off and do things like take other classes and be responsible and stuff. So don't worry about the fact there's no people actually sitting here. I think it's the first time that I've lectured to an empty classroom, so maybe I'll be lecturing to the camera more than usual. But we're going to get through this. This is actually some pretty interesting stuff, and some interesting video at the end, too, to look forward to. Though you can contemplate at home, what is this? What is going on here? What are we looking at? And yes, it has something to do with the sun. What is it? Okay, so this is Physics 1600 Introductory Astronomy. We're talking about the sun's interior today, and actually gravitational lensing, G-lensing, and apods too. Next time we'll be doing stars. So the whole point of this is to go out into the universe, away from our solar system. But in order to understand other stars better, we have to understand our star better. So first we understand our star, then we go to other stars, then we go out to galaxies and the rest of the universe cosmology, some really fun stuff. These lectures are taking place at Michigan Technological University. I am Professor Robert Nemiroff, and if you want to get credit, you want to go to courses.mtu.edu. You don't have to ever attend this class, as today we have no one attending because it's occurring at an unusual time. Still, the material being covered today is important. And you should look at this video and remember what I say, or remember the highlights of what I say, and be able to regurgitate them with showing understanding and compassion on homework quizzes, and hopefully the midterm, which is already due, and the final, which will come up at the end of the semester. So you're also responsible each time for the listed Wikipedia entries, but not if they go into the higher math, just the ideas and the key points. And you're responsible for all the astronomy pictures of the day, APODs, that occurred during this course when it's being taped, which is the fall semester of 2008. I understand these are reviewed again in the spring and even summer of 2009. So hello to the future of the people watching at those times. And around the world, too. People watch this. Get some email. Don't have, it's not like a major TV show, but we do have some followers. Let's see, this past week I got email from Alaska, and where was that other place? One of the islands of Japan. Someone is following this course and emailed me with something. Hello to you. Okay, so today, though, we are covering the sun. Look at the sun again. Look at solar core on Wikipedia. Look at proton-proton chain reaction, and look at gravitational lens. The entries as they appear on Wikipedia, or as they did appear in the beginning of the semester 2008, fall 2008. Okay, so the sun's interior. The sun has several layers, sort of like the Earth does. But the sun doesn't have a solid surface anywhere. So as I said last lecture, you can't land on the sun. As you go into the sun, it gets hotter and hotter. And the hottest part is the core. In the core, hydrogen is fused into helium, which gives the energy of the sun. Now for a while, for a long time, humans didn't know, nobody knew how the sun was powered. How do you power this sun? Why is it so bright? How come the Earth isn't as bright? Different hypotheses were created. As science progressed, one thought was that it's gravitationally contracting. Before that, it were things that were essentially non-scientific. But gravitational contraction, which does heat part of Saturn and Jupiter, and is the reason why Saturn emits more light than it receives, but that's not primarily what powers the sun. What powers the sun is something called fusion. Fusion is when you take lots of smaller things and you fuse them into a larger thing. In this case, the primary thing that happens, I think the only kind of fusion that happens in any large scale in the sun, is nuclear fusion of hydrogen into helium. So outside of the core, which has the hottest energies, so you need the hottest energies to do fusion. Fusion will only work when it's really hot, because hotness means fast-moving things. Fast-moving things in the sun mean fast-moving atoms and molecules. And when the atoms and molecules are moving fast enough and they hit each other, then usually they glance off. But if they're moving fast enough, they stick. And if they stick, you can get more massive things. And then they start releasing energy because the things that stick together in really dense formation. And they emit light. We'll see more of that later. Okay, back to the outer parts of the sun. Outside of the core is a radiation zone where energy is transferred from the fusion-dominated core out to the outer parts of the sun by radiation, like light, mostly photons. Outside of that, there's a convection zone. Convection is a kind of transformation when there's big blobs of stuff moving around. It isn't just little photons of light, but big portions of the sun are actually moving. One common type of convection, probably the most common type of convection that you see with your eyes, is when water boils. So there's particularly hot parts of the water that move around. You see bubbles. The bubbles, I think, aren't necessarily, they're sometimes air, but they show that there are boiling parts of the water. There are convective parts, bubbles of things that move around, bubbles of hot material that move into the cold material and thus heat the hot material. So convection is, okay, on to the next one. Here's the convection zone here. Here's the core, the hot core. Here's the radiation zone there. So here's an even more detailed image of the sun, taken originally from Stanford, but went onto Wikipedia through public domain. So thermonuclear fusion again happens here. The core temperature is about 14,000 degrees Kelvin. I like this very detailed image here. Out to less than 14 million degrees, there's 14 million there, out past 1 million degrees where the convection, the radiation zone dominates there, out to the convection zone where large portions of solar material bob around and the hot part moves out, the hot bubbles move out, and the cooler stuff moves around the bubbles and sinks in. There's turbulent convection up near the surface of the sun. Then the part of the sun where you can see is called the photosphere. I explained this last time. So the sun doesn't have a surface, but it has a part. The sun becomes increasingly dense as you go down. As you go down, it becomes so dense and so hot that eventually the electrons are knocked away from the protons. And when that happens, photons can't go very far, and they bounce off. And so the photosphere of the universe is called the microwave background, but the photosphere of the sun is called the photosphere. And it is where we can't see further in because it's too ionized. Now, there's lots of high-energy radiation leaving from the center of the sun through nuclear reactions. And those gamma rays, they start as gamma rays, bounce around and eventually will make their way out, being cooled by the rest of the sun, out from the photosphere at some point. Of course, there are photosphere photons that go like this, too. So the sun emits all kinds of light, all the way from the radio emission all the way to the gamma ray emission, including optical light, which is a peak for the sun, and ultraviolet, infrared, and visible light that we can see. So reviewing also, here you can see X and gamma radiations coming off of there. There's sunspots shown here. There are coronal holes out further depicted there. Neutrinos, we'll talk about later, come from the center of the sun. Here you see a prominence. It's not very dense, but it can make the sun look significantly brighter. So here are the different zones of the sun. It has been confirmed relatively recently that even on the surface of the sun, and certainly interior to the sun, there are large-scale rivers, large-scale convection currents, not only bubbles that move out, like in solar granules and in the convection part of the sun, but there's big areas where the sun essentially flows like a river. Here you can see on the surface of the sun, there's parts where this the sun flows, and inside they do loops. So it's relatively recently confirmed that the sun does things like that. The sun is being a very complex object. As I said before, the outer parts of the sun give us relatively constant amount of energy. The sun isn't becoming twice as bright. All of this violence that we see, these explosions, they don't take up much of the sun. On the surface of the sun, they don't make the sun that much brighter. In the center of the sun, there are these tremendous continual nuclear explosions going on, but they're so continuous, it's not really an explosion, it's a continuous event. And it's relatively steady, and it holds up the sun. It provides the pressure so the sun doesn't collapse down on itself. And it provides a lot of the heat that heats the rest of the sun. Here you see the sun oscillates. The sun can ring like a bell, and actually these relatively cool and hot areas, they raise and lower the surface of the sun very slightly. And this occurs on the time scale of minutes. And these are only some of the solar oscillation modes. The sun rings like a bell in many ways, with many different wavelength waves going around the sun. But if you can detect it, the sun itself also oscillates back and forth, even in relatively small regions. Okay, so what happens in the very center of the sun? Now, different stars, when we go out into the universe, we will find that different stars have fusion that lights them up in different ways. There's the carbon, nitrogen, oxygen cycle. But the sun is not massive enough to do that. The sun is massive enough to do what's called the proton-proton nuclear chain reaction. So here we start off, down here it shows that the protons are red and the neutrons are gray and positrons are white, but that's just to show you what's going on. They aren't really that color. Gamma rays are shown by the gamma ray signal, and neutrinos are shown by their Greek symbols. So in the center of the sun, you don't have hydrogen atoms, you have hydrogen nuclei, which are protons. So there's lots of these protons moving around everywhere. You also have electrons moving around, but they're not shown here. They're not all that important right now. The most important thing are protons, and so sometimes everything collides, but sometimes protons collide with each other, and boom, they're moving fast enough because the sun's center is hot enough to create a nuclear reaction. And this nuclear reaction makes two protons move into a proton and a neutron, and a positron comes off. A positron is like an electron, except it has opposite charge. So if a positron hits an electron, they annihilate, and you get gamma rays moving off. But here we have a neutrino moving off. Now this neutrino will be important later, because the center of the sun is an important neutrino source, which helped us figure out what's going on in the sun. It helps us understand particle physics as well. So many places inside the sun, there are protons bouncing into each other, banging into each other so violently they stick through nuclear fusion. So here's another one happening over here. This happens all through the inside of the sun, and it's very sensitive to the temperature of the sun. So in the very center of the sun, where it's the hottest, there's the highest proton-proton nuclear reaction rate. So since there's lots of protons moving around, the daughter product of the previous proton collision is another version of hydrogen that is proton and a neutron, and that will then collide with another proton. You know what? It collides with all kinds of stuff. But when it collides with other stuff, it doesn't give us another interesting daughter product. But this one does. When it collides, when a proton-neutron, a nuclear entity, collides with, has a name, but it just wouldn't be useful to know it right now, collides with another proton, you get another nuclear fusion reaction. They fuse to form something heavier with a form of helium, and a gamma ray moves off. A very powerful gamma ray moves off of that one. And since this is happening all over the sun, it's sure to happen somewhere else as well. And now we're left with mostly protons again, but now we can see that there are helium nuclei that have two protons. The number of protons tell us what the element is. So if it's got two protons, it's helium. It has another nucleon in it, a neutron, which doesn't have charge, so it doesn't make it into the next higher element, which would have been lithium. So eventually, these guys will collide. Now, yes, they're going to collide with other protons first, but those aren't generally interesting. It's most interesting when these things collide with another entity like them. When that happens, many times, you will have protons moving off, now liberated again. So they'll go back and run around the sun and collide with other protons and hopefully become involved in another chain reaction. But then you get this. What is this? This is a stable helium nucleus. Helium-4, 2 protons, 2 neutrons. It did not exist before. So this is solar alchemy. An element has been created that did not exist before. Helium, stable helium. And this stable helium then exists in the sun where it did not before. So in the center of the sun will fuse hydrogen and helium until it can't do it anymore. And the sun will move its center from being primarily hydrogen to being primarily helium in its center, and giving off a lot of energy. Most of the energy will be coming off as gamma rays here. The neutrinos that come off don't generally carry that much energy. They do carry some, but the interesting thing about them is that we can see these neutrinos directly. We can't see the gamma rays directly. The gamma rays are going to go bouncing into other protons and neutrons, usually protons, and possibly electrons and positrons, and they will bounce around for a long time, 100,000 years or so, before the daughter photons from that gamma ray photon ever make it out of the sun. But the neutrinos will fly relatively free, and we will see those. And we will see also, well, eventually the more massive products will become evident. So let's talk about the neutrinos now. Nuclear fusion will create neutrinos as well as helium in the proton-proton chain of the sun. So we realized this, decades ago, and so people started trying ways of finding these neutrinos that were coming out of the center of the sun, because that would confirm, for one thing, that there is nuclear fusion going on in the center of the sun. So they built these expensive neutrino detectors. They didn't find anything. They didn't see anything. So either the sun wasn't producing nuclear fusion in the way they thought, or it wasn't producing neutrinos in the way was thought. So they made even more sophisticated experiments, in second experiments. And the good news is that these experiments did see neutrinos. So we weren't totally off base. We do understand the solar temperature profile. We do understand the solar model. We do understand nuclear physics well enough to know that neutrinos are coming off the sun. But they were just fewer than we expected. And that, again, was a mystery. So many times in science, when we find something out, we solve old mysteries, but at the same time, we make new mysteries. And that was the case of the solar neutrino experiments. First, they didn't see any. Then they saw too few. Then, the most recent ones, and we'll see pictures of these reactors, they saw neutrinos of different types. So what we learned was that there are different kinds of neutrinos, as has been postulated. There are electron neutrinos, and there are tau neutrinos, and even other types. And these neutrinos can change into different types. And that was not expected that would happen, because the standard model of particle physics didn't think that massless neutrinos could change type. But it turns out that we now think that neutrinos have a very slight amount of mass. Too little mass to be important generally in other ways. But this little mass enables them to change their type by bouncing or being affected by magnetic fields or other fields or other particles on the way out of the sun. So here is one of the neutrino detectors that didn't see as many neutrinos as was thought. This is the Super Kamiokande detector in Japan. And this is a huge vat of cleaning fluid. Sometimes there are places that you can use water. And there are lots of photomultipliers around here that look for light, so that when a neutrino comes into this vast pool of cleaning fluid and hits something, it will emit light that will then be detected by these detectors all around. And that will then tell us that a neutrino came in, and we can measure neutrino rates and energies from those reactions. So here's a raft of people right here. It shows you the size of this internal detector. They are looking at the photomultipliers here, trying to see, maybe they're installing them or trying to see what's wrong with one of them. Okay, in 2003 or so, an important verification came where the Kamland experiment, here you see actually created neutrinos close enough to Kamiokande so that Kamiokande could see, Super Kamiokande could see the neutrinos from Kamaland. And that verified that it worked, that all of this was not just fictitious. Whenever you have an experiment, it's really important to be able to calibrate your experiment, to see whether it's seeing what you think it's seeing, to see if it's as sensitive as you think it is. And so here, this was a really important thing, being able to generate the neutrinos ourselves through a common nuclear reactor, and being able to see them with the nearby neutrino detector really helped us confirm that we were seeing what we thought we were seeing. Another way is by actually melting long holes in the ice of Antarctica, the clear ice of Antarctica, and dropping in, instead of putting your detectors around here like this, you drop the detectors into deeply melted holes in Antarctica, and you look for neutrinos to hit the very clear ice of Antarctica that has very few bubbles. And then when the neutrino hits there, it gives you a photon signal, and that photon signal is then seen by these big photon detectors. And what happens is, after these holes are melted and these things are dropped in there, they are then refrozen. The water seeps in and refreezes around them, but that's okay because they're now electronically connected up above. So this was also an important experiment in determining solar neutrino rate. The Sudbury neutrino detector in Canada was actually one of the ones that really broke open the game to prove that we are seeing neutrinos. Not only are we seeing neutrinos, but we're seeing them of different types of neutrinos. We're seeing, so all the neutrinos were pretty much accounted for, and the lack of electron neutrinos that were being seen by the previous experiment was explained. So this is a really cool underground sphere. And so here you see a person standing under it. And here you see this sphere actually being built early on, the Sudbury detector, which has now reported the missing neutrinos. So we understand the energy source of the sun. This is actually a picture of the center of the sun. We don't have in neutrino telescopes any kind of angular resolution practically at all. So it's this bright spot. The center of the sun is seen as a bright spot in neutrinos, and we're happy we can see even that. Okay, so let's look now, take a step into something that's slightly different but is really cool, which is gravity lensing in the sun. And what ties these things together is that the sun itself is important for understanding gravity, in particular gravitational lensing, because the sun was the first gravitational lens ever detected. And this was detected in 1919 by an expedition by Eddington and others. And it was there, they were looking at a total eclipse of the sun to try to see if the stars behind the sun shifted position from when the sun wasn't in front of that part of the sky. So when the sun is not in front of a part of the sky, you see stars. Then, during a total eclipse of the sun is there, and the moon is blocking its light, and you still see the stars. But now there's this massive sun, which is causing those stars to slightly appear slightly further out than before. And by measuring exactly how much further out, you can detect the mass of the sun, and you can confirm the type of gravity, the theory of gravity, or class of theory of gravity that is doing that. So this was all due to Einstein. Einstein's first prediction, actually, even if it wasn't for Einstein, people would predict that gravity deflects light and the sun would be a gravitational lens. But the amount of the sun being a gravitational lens was predicted by Einstein. And the first time he predicted it was in 1911. And he came out with a theory that, gravity theory, and this gravity theory had light being deflected by the sun, and the problem was that this theory was wrong. And the amount of deflection of light by the sun predicted by Einstein's 1911 theory was only half of that by his later theory. And people went out and tried to test Einstein's prediction. There were attempts to test his prediction, and if they had tested it as accurately as they had in the decade that followed, Einstein would not have been as popular a name as he is today. That they were not able to do it because World War weather and World War I got in the way of accurate predictions, of testing their predictions. Einstein then came out with a more sophisticated theory of gravity in 1915. And this predicted twice the amount of deflection of light by the sun as his previous theory. And then expeditions went out, were actually able to measure it, and they were able to confirm that prediction of Einstein's general theory of relativity. And Einstein, instantly already famous, became a superstar and is now, he has had many, many wonderful things that he's predicted. And gravity might have been one of the hardest ones to get right, because everybody's been trying to study gravity, because gravity is an obvious feature on the Earth. And he revised it. It's not that Newton was so much wrong. Newton did the best he could with the data he had. And Newton's theory actually is used to explain almost all of the solar system as we know it. You really have to look in detail most of the time to see the differences between Newton's theory of gravity, which just goes like F is equal to gmm over r squared, and Einstein's theory of gravity, which essentially shows that you can model gravity as a geometric concept, and that things all follow the same geometric trajectories. Okay, here is a cartoon, sort of. Here's the Earth, where we will see objects. So we have eyes here on the Earth. Let's make an eye, or a radio telescope, or a regular telescope. So here is this object here. No, here is this object here. This object emits light in all directions. Some of the light just hits this. That's not interesting. The light that's particularly interesting is the part that's bent around to come to the Earth, because that object looks like it's over here. So it is not where it appears to be due to the lens nature of gravity, in this case the sun. Now we have all kinds of lenses. I have glass lenses that deflect light in a much more common way, but our sun can use its own gravity. It's a huge lens and creates very interesting effects on background light. And so here's an image of the sun, and during an eclipse you see the corona. An eclipse, here you see the sun just as a picture, and superimposed on its background field. So what happens is, when the sun isn't there, you see this field, but when the sun is there, the stars are all slightly pushed out from the sun because they're being deflected by the sun. Now, the stars themselves don't care. They're far away. They're not really being pushed out. It's the image of the stars that we see that are being pushed out as seen on the Earth. So here you see the Pleiades. Okay, moving along. This is an image of what would happen if you push, what happens when the sun gets near a star. It actually pushes its image out slightly. We have a hard time seeing this because this only occurs in any large amount right near the limb of the sun, near the edge of the sun. And it only occurs on very small scales, on an arcsecond or two. But this image is showing that in some clear detail. Okay, here are some movies that I made. I put them on Astronomy Picture of the Day as Too Close to a Black Hole. So these are cartoons, but they show the much larger gravitational lens effect when you get near a black hole. So the sun has a small gravitational lens effect that we've seen. So as I like to say, the gravitational theories, or general relativity, may or may not be correct, but we know for sure that gravitational lensing is correct because we can see gravitational lens deflection by our sun. So in this cartoon, we have the Belt of Orion here, and we have Betelgeuse here, and here we have Sirius, and I think this is Rigel. But if you put a black hole here, it will push these things out. So it pushes it out because the images that come, wouldn't you think that gravity would attract light and therefore detract images? Yes, it is attracting the light. But because then the images that you see have to go further away from the sun to get to us because they're attracted to the sun, we appear to see the images pushed away. So here you see the black hole would be here. We won't see anything from this region. Here's one image of the Belt of Orion. Here's another image of the Belt of Orion. Here's one image of Sirius, another image of Sirius, one image of Betelgeuse, another image of Betelgeuse. It turns out that compact gravitational lenses create more than one image of the sun. In fact, they create an infinite number of images, but two relatively bright ones. Our sun isn't compact enough to create a discernible second image of the sun, or background stars. Okay, so I created a paper that's in the American Journal of Physics that can be looked up. in any library. It's also online, although you might need a subscription to see it. However, I've made the paper that discusses these effects into a movie, and I will show some of these movie features now. Or you can download this image, this paper from the World Wide Web. You go to black holes, actually. You can find this on the web by searching for black holes and looking for the words virtual trips to black holes and neutron stars. And that should come up on the first page. You can download this paper and read the different parts of it. But I will show you some of the movies of what it's like to approach a black hole, for instance. So I will click on that, and then my Windows Media Player will continue to do the same movie over and over again. So here's when you're far from the black hole. You see the original image. Here's Orion, again, as we saw. But now I'm able to go and step into the black hole by going closer and closer. This is telling us how close we are in terms of Schwarzschild radius up there. So we're 60 Schwarzschild radii away. Now we're 48. And now you can see in the center, there's a region where you can't see anything. Yes, that's the most popular part of the black hole that's actually black. But the other parts that I'm interested in is right around there where you see strong gravitational lensing effects. So right here, you're seeing the second image of Orion coming up. And you can see the second image here. It's the second image of Sirius. Here's the second image of Betelgeuse. The outer image of Betelgeuse, the interior image of Betelgeuse. So as you go closer, you can see all of these things growing. The black hole, well, it's essentially the event horizon growing where the region of black where you see nothing. Nothing comes from the black hole. But multiple images of other stars. Around here, there's a circle that divides the outer image set from the inner image set, and that's called an Einstein ring, after Albert Einstein. So here we're going up. We're going to go to 10 Schwarzschild radii. Schwarzschild radii is the radius of the event horizon, right here. Okay, so let's get rid of that. And now we're going to circle the black hole at that distance. Again, it moves very fast, so we see, let it go around once or twice so you get sufficiently dizzy. And then I'll stop it at the beginning. Stop. Okay, let's back it up. Okay, so here we are where we were before. Here's one image of the belt of Orion. Here's another. Here's one image of Sirius, another. Betelgeuse, Betelgeuse. So now, as we do an orbit around the black hole, you can see that these things appear to move out, and this appears to move in. And the images of Sirius and Betelgeuse are always exactly connected around through the center of the black hole. Okay, and you can get many more details there at the website. So let's approach the photon sphere of the black hole. I'll go through these pretty quickly. Okay, let's freeze that one. So we'll start out far from the black hole. Now we're going to go right into 1.5 times the Schwarzschild radius. And the black hole appears to get bigger and bigger and bigger until it takes up fully half the sky. When it takes up half the sky, everything below you is dark, and you're at the photon sphere. Photons can do orbits around the black hole at the photon sphere. So here it becomes bigger and bigger and bigger, and eventually you're at 1.5. And everything below you is dark. And there is still a sky above you, though. So we'll look up and see the sky above you. Everything above the photon sphere is still there. Here we look up. Let's freeze it again. So here it's dark, looking up. No, I have to look up pretty much to see it. I have to look up a lot to see it. Okay, here we go. Looking up a lot, starting to see stars in the sky. So soon we're going to look directly along the photon sphere. There it is. Okay, now we're going to orbit the black hole at the photon sphere. That looks really cool. This is the coolest movie of the ones I'm going to show today. So here we see it. Everything below is dark because that's the black hole. Photons can't come to you from the black hole. Photons can come to you from above, though, and they get distorted by the gravity of the black hole. Sometimes they have to do circles around the black hole to get to you. So this is the image right here of the Einstein ring. There, that's the first sky Einstein ring. So as you go around things appear to move very strangely. You have to read the paper to understand why. But you will never see an image cross the Einstein ring here. That divides image sets. Okay. Okay, so let's minimize that. And that will conclude the lecture part. So we did the interior of the sun, and we did some gravitational lensing effects that around the sun and around black holes. So now I'm going to review the astronomy pictures of the day for the past while. And there'll be more than the past week, but only up to today, because I haven't done tomorrow's yet. And Jerry hasn't done Wednesday's yet. So we'll keep going. We will minimize this. We will bring up back to that, except now we're going to go to apod.nasa.gov and see today's astronomy picture of the day, which we will get to. But we have to go back into the archive and start on October 9. We're going back that far because we haven't reviewed these yet. The midterm got in the way. There were no classes last week. Okay, so this is the mass of stars in a star-forming region known as NGC 6357. So this is a classic star-forming region. We showed these a lot on APOD because they're so cool looking. They have these amazing dust sculptures, these dust mountains that are being eroded away by massive stars. You see young stars, you see blue stars, you see stars of different kinds and colors. And so this star cluster, Primus 24, I guess is here. Primus 24 in particular has very massive stars, some of the most massive stars known. So this star-forming region, star-forming regions usually have massive stars. They then blow up in supernovae and go away. But when you see stars being formed, you can be pretty sure the most massive ones are much more massive than the stars around the sun, because the stars are not being formed right around the sun. And this is 50 light years across, 8,000 light years away, and creating very massive stars. Exactly why very massive stars are created has something to do with the chemical elements available, the trace elements beyond hydrogen and helium, which compose most stars, but the details are not well known. Okay, the next one is an irregular galaxy. So when we study galaxies later in this course, we will see that many galaxies are shown to be spiral or elliptical, but some of them are not so easily classified. And this one is an irregular one. It looks a lot like the Large Magellanic, it's thought to look a lot like the Large Magellanic Clouds. So this spans 50,000 light years and lies 180,000 light years away. Oh no, the LMC is 180,000 light years away, but this NGC 55 is 6 million light years away. So you can see lots of stars. This is star-forming regions here with the bright stars in them, because the bright stars tend to be the most massive. Sometimes they're shrouded by dust, but many times they break free, or some of them just aren't there. So you just see this unusual galaxy called NGC 55. Okay, many times people get together in parties late at night, called star parties, to look at things on the sky, constellations. Of course, you don't need a telescope. When you go to a star party, many times it's really cool because people have some big telescopes there, and they'll be more than happy to show you open clusters, many times globular clusters, nebula, and sometimes some of the star-forming regions that you've seen here. Many times the Orion Nebula, if it's up, if it's visible. So here, one of the interesting things about this, there was a camera set up, and you can see the star party going on here. You can see Orion. Here's the stars in the belt of Orion. But what's particularly cool, there was a really bright fireball, sometimes called a bolide, that came in and was caught by the camera. So it was unusual to find. The person said they saw it light up. They thought somebody was turning on their headlights. Now, what's interesting here is, well, so it's not that unusual to see a bright bolide. What's more unusual is to predict that one's going to happen. And a very tiny asteroid called 2003 TC3 came in to the Earth a few weeks ago. And it was a couple weeks ago. And was unusual in that it was predicted. However, it wasn't well photographed from the ground. Yeah, I think there is some indication that it was seen, even from the ground, it was seen by satellites. And many times when we predict that something's going to hit the Earth or something's going to be near the Earth, it's going to miss the Earth. And it's exciting when it gets inside the orbit of the moon. This thing was actually predicted that it was going to hit. It didn't cause any damage. It probably broke up in the Earth's atmosphere, and probably no big parts of it hit the ground. Okay. Going to the next one. This is a big, beautiful spiral galaxy called NGC 3370. So our own spiral galaxy looks a lot like this, except it has more of a bar in the galactic center. So the only thing this lacks is a bar, but it has a lot of the same kind of spiral features that our own spiral galaxy has. And I would expect that our own galaxy, of all the galaxies I've seen outside of the very central region, this probably looks most like our own galaxy. So this was taken by the Hubble Space Telescope, in particular one of their cameras, most sensitive wide-angle cameras called the Advanced Cameras for Surveys. Advanced Camera for Surveys. This was studied because in 1994, there was a Type 1a supernova explosion. And the Type 1a explosions are particularly interesting because they help us calibrate the distance scale of the universe. This is known to contain Cepheids. So this is close enough to contain Cepheid variables which help us calibrate its distance. Okay, let's see, spring moon. Okay, in October 13th, a little more than a week ago, the Cassini spacecraft that's orbiting Saturn made a second flyby of Enceladus, which is it's one of its stranger moons. I guess Titan is the strangest moon, but Enceladus is the unexpectedly active moon. And Enceladus is spewing ice and water vapor. And it wasn't predicted that it would do that. And it's indicative of underground oceans. And underground oceans are places where there might be life. So Enceladus soon became one of the candidates to look for life in the solar system. Now, in this flyby, they were attempting to find out what the surface features are. They flew right by a flume, one of the plumes. It could well be that this grayish stuff is water vapor evaporating into ice crystals right off the surface of Enceladus. If so, that's an amazing thing to have caught and to study. Okay, it is thought that most of the water vapor comes out of these tiger stripes, or in the tiger stripe regions. These are relatively young regions because they have relatively few craters. Here you see a crater here and a crater here, but you don't see many craters. You just see these vast regions that have all these grooves on them. Now these grooves might look here to have lots of dots on them, but that's just an image artifact. That's not real. This is one of the tiger stripes, and it's casting a shadow to make it look relatively large. So it's a very interesting tiger stripe. Okay, going to the next one. Here you see Orion rising, taken by a camera, so we already saw it in previous images. So here you see the belt of Orion. Here you see Sirius isn't seen here, actually. This is Betelgeuse. I think this is Rigel. I think it says down there. Is it Rigel? Yes. And here you see, in the belt of Orion, the Orion Nebula, which is a massive star-forming region that they were able to take up close. So it's a very interesting picture. This is just taken with a camera. Okay, due to the amazing optics that are available now from the ground, we can take images of things that would just appear to be blurry messes before and resolve them. This is the International Space Station as captured from the ground by an amateur. And superimposed, caught, I guess several days later, was the Tyros 2 satellite that was launched in 1960. So it's possible with the right telescope to get images of old satellites and new ones as well. Actually, they were launched at different times, so this one was captured by image later than this one. Okay. Satellites break up when they come to Earth, and here we see the European Space Agency's Automated Transfer Vehicle, which is a robotic spacecraft intended to deliver cargo to the International Space Station. This crashed to Earth, and we knew it was going to happen. It was controlled, and it broke into pieces in a most spectacular way that was photographed. This one, I think, comes from the air in a high-definition video. And you can see many of the particles of this spacecraft just break up and cause their own little meteors. So it helps us to understand real meteors and what real meteors are composed of, to watch something that we know of. This is a controlled experiment. This helps us to understand our solar system by doing a controlled experiment and something breaking up in the Earth's atmosphere. Okay, this is another star-forming region. Has many of the common features of star-forming regions. Vast amount of ionized gas that is glowing, a open cluster of stars, dust created by the young stars, and dust pillars that are being burned away by the young stars. And this one is called Sharpless 171, and it's only 3,000 light years away. And, okay, this is another star-forming region, but this is a much closer up image of one. This is in the Lagoon Nebula. And what's cool about this is that there's these funnel-shaped things that were not predicted beforehand. And these things have something to do with the star formation going on. There's young stars here. These young stars are made more red by the thick dust that's all around. So this dust is being burned away by the bright young stars, but there's some very active stuff going on here involving funnel clouds or whirlwinds, and we're studying those to understand better what's going on. And I will conclude today with today's image. Shows that there are things unknown here in our own solar system. This is again Cassini. Cassini now not taking a picture of one of the moons of Saturn, but of, well, four of the moons of Saturn actually, but Saturn itself looms large in this part of the image. This is Titan. Titan doesn't show any craters in optical light. There are other moons. I don't remember what they are. I think there's 4 here somewhere. I can see 2, but I don't see the fourth. The bottom part of Saturn is well known. This is the ring right here, the ring plane, which is very thin. It's razor thin, the ring plane. And it only appears thick when we see it on edge. Here we're seeing it nearly on edge. Well, it only appears thick when we see it not on edge, and we see it. But here it's almost lined up, and so it almost has totally disappeared. But the light coming from the sun has made it cast shadows here. Here are the shadows of the rings on Saturn itself. And we think that the strangest thing about this is the unusual colors in the north part of Saturn. So we didn't expect these colors so much in such detail, and we're trying to, planetary scientists are trying to understand how possibly the change of seasons and the light through the rings has caused these different colors to appear in Saturn's atmosphere. So Saturn's atmosphere is still under study, and new images, even from Cassini, are still showing things we don't understand. Okay, so I will do Tuesday and Wednesday, October 21st and October 22nd next week. They will be added to next Wednesday's review. But that will conclude today's lecture, and I will see you next Monday. Bye for now.